First, I want to do a quick calibration. How many of you have heard of a DATAO? Okay, and of those of you that have heard of us, how many actually know what we actually do? Okay, all right, so it's relevant to the talk because I have to tell you what we're doing with distributed deep learning on Spark and Tachyon. I think, okay, I'm not gonna ask how many people have heard of Spark, but how many have heard of Tachyon? Cool. So this talk actually going to be heavily focused on the Tachyon aspect of our architecture. There's some really interesting architectural points of view that I want to share with you. And so what I'll do is I'll go through, I don't want to just start showing you charts and graphs and so on. I'll share with you what we went through in terms of what we do at DATAO, some of the use cases that we've come across and that we determined that they're best served with deep learning. And in the process, how we arrived at some of the architectural decisions and where Tachyon comes in, how we address these, and then share some of the lessons. I'll try to leave enough. I love taking questions, so if necessary, I'll skip through some of the slides so we can have more time for questions. So along the way, as I discuss these things, you'll hear how some interesting things come about, some of these decisions are made, where some of the things that you may not think about a lot, for example, data center network fabric, where that's going and how that's relevant to Spark and Tachyon, and how some of these engineering architectural decisions are made. So with that, I'll share with you a little bit. I'll show you what a DATAO does and in what context we have the predictive analytics. So at a DATAO, what we do is we do what I call the iPhone for big data. In other words, it's time after the big data layer and the big compute layer like Spark are in place, then it's time to take a look at the world top down from the human user point of view, the data scientist, the data engineer, and the business analysts. These people need to be able to collaborate, and they need to have natural interfaces. And in this case, I'll show you typing in natural English, right, natural language, to ask both aggregation questions as well as predictive questions. And so that's the third pillar of our product, predictive analytics. Okay, so let me switch over and show you what that UI looks like. Okay, so this is one user's view of a DATAO software. So it looks very much like Google Docs, which is, I ran the Google Apps operations team at Google. So a lot of it is heritage. So here, these are what we call narratives. And if I open one of them, I can open this up. And this is what a business user would see of a DATAO software. You can think of this as document, charts, and graphs, and text. And within this document, we want people to be able to interact with data naturally. So today, we have a Spark system running live in Amazon. And this is already connected. I think many of you, how many people are familiar with this data set, the flight info data set, right? So this is published by the Department of Transportation. We use this for a lot of demos. So you can just say, right, show first 5 rows of data or 10 rows of data. So this is very natural. Oh, I put the cursor in the wrong place. But that actually executed in real time. It went into the cluster query Spark, called the API, the data comes back. And so next you can ask aggregation questions like, show relationship between arrival delay and day of week. So what this will do is aggregate in real time about 123 million rows of data, 124 million rows of data, and tell you over the 20-year period which day of the week has the highest average delay. Right? So these are sort of the affordances that we provide to our end users. Okay? Now the really cool thing is, where's the predictive analytics? I should be able to, as a business user, ask questions like this, right? Forecast, arrival delay in the next 30 days of, say, flight date, right? And so what this will do is run a machine learning algorithm in the cluster. So this one is a fairly simple machine learning algorithm. It's Holt Winters It has 3 components to it. It has the level, the trend, and also the seasonality. There's a bit of data, so it's going to take a bit of time to run. There we go, it's done. So this is the fit, the actual data, and then the forecast. Okay? So as we develop these things, our customers ask for more and more of these predictive capabilities, and so we come across these use cases that can be solved using existing machine learning techniques, but are actually quite naturally fit for deep learning. Not just because it's sort of the latest and greatest hot thing, but these are cases where deep learning are uniquely suited. For example, in the IoT space, there's predictive maintenance, customer segmentation. Instead of some experienced VP of marketing saying we should segment based on these features, age, income, and these are the ranges, these thresholds and so on, we can embed customers' behaviors into a, say, 700-dimensional space and then cluster them that way. It's called embedding in deep learning and fraud detection and so on. So if you can imagine how what I just showed you, how that works, essentially it's a vertically integrated stack all the way from the UI down to the algorithm and the big compute, which is the Spark engine. We also support Flink and so on, down to the data. Then that begs the question, how are we going to support deep learning? What's different about deep learning? Well, the first challenge is, how many of you have started looking into deep learning? I mean, not more than just reading, right, exactly. So you're very familiar with this question, right? For example, there is the current push and pull between CPU and GPU. And then you could go as far, you can continue GPU, FPGA, ASICs, and maybe even neuromorphics. So for a company like a Data, what is the appropriate platform? So that's the first challenge. And what do you think is the right answer to that? Well, the right answer in all cases is it depends, right? So the right answer to the question is that it depends on the context and the parameters in which you operate. So let me share with you an analogy. Of course, we've all heard of MapReduce. How many people are familiar with Prego? Right, giraffe, right? So Prego is a graph processing distributed infrastructure developed at Google, and it's open source as Giraffe. And when I was at Google, I sort of had this puzzle. Basically, almost all workloads at Google at the time, in any case, was done in MapReduce, right? And then if you think about Prego, Prego is a graph processing algorithm, right? And if there's one classically appropriate graph algorithm, it is PageRank, right? PageRank is inherently graph, and yet, when Prego came along, Google didn't switch over to say, we're going to move away from MapReduce model, we're going to do a Prego. Anybody want to guess why? Inertia, right? Yeah, well, I think inertia is right. But I think the more general answer is that there is a lot of economies of scale in the billions of dollars that's already been invested in the MapReduce infrastructure, right? So this is one of my favorite quotes from Sanjay Gamawat, right? If you squint at a problem just a certain way, a lot of them become a MapReduce problem, right? And so there's an economy of scale of continuing to invest in that infrastructure. A lot of people, we think about just machines, but programmer productivity is also very important, right? So there's an analogy here. So this sort of, along the way, you'll see me show the aha moments, right? Some of the ideas that are a little bit non-obvious, but makes a lot of sense once you think about it a little bit more deeply. So there's an analogy here that applies certainly to a data, to our customers. If you think about the Spark ecosystem today, right? I'm really excited. I remember 3-4 years ago when we were just trying to convince people to look at Spark, and they said, well, it's too immature. So today we face a different set of dynamics where a lot of people have already invested in the Spark infrastructure. And for us to go in and say, okay, now buy some GPU machines, that doesn't make any sense, right? They just want that to be another workload. They just want deep learning to be another workload. So that, if you look at the data infrastructure there, the blue stuff is all our proprietary software, And underneath that, there is the big compute, Spark engine, for example. We also support the other ones. So if our customer already has Spark, then it makes a lot of sense to say, you know, I can just send in another jar, and you can run the deep learning job that way. All right, so that settles sort of the first challenge. Okay, so the moral here is that there should be no religion in engineering. Architecturally, choices are essentially locally optimal. So what's best for me is not necessarily what's best for you. Right? So it's important to remember that because we do get into a lot of arguments about one engine is 20% faster than the other, and forget about a lot of the I would say economically more important decisions to be made. Okay, so once we've decided it's going to be Spark-based, then you got to take a look at how deep learning is different from some of the other algorithms that might be implemented in a distributed manner. So this is how many people are familiar with disbelief? This is the one deep learning infrastructure at Google that was published, distributed belief. So the way you can sort of dissect this is essentially look at the green and the blue. Okay, so this one is a highly distributed infrastructure in multiple ways. It's certainly data parallel, right? So when your training data comes in and is sharded into a whole bunch of data shards, the model is also parallelized, right? The model, that's sort of unique about deep learning because your model can have millions or even billions of parameters, whereas the other machine learning techniques that we use may be 10, 20, 1,000. So therefore, in many cases, you have to distribute the model itself, not just the training data. So here, there's a model replica layer. So that's where the model is stored, and then there's a green layer there called parameter server. And so if you're familiar with gradient descent, essentially these are the two steps, right? Deep learning, as complicated as it may be, is essentially one of the algorithms, the backpropagation is gradient descent. First, you backpropagate the errors, and that's the errors in terms of gradients, and then so that's the compute the gradient step. And the next step is then you essentially apply the gradients to your existing parameters, and then you update the parameter set. So it's really just these two steps, the gradient step and the descent step. So in the case of disbelief, the gradient step is done in where the model is, and then it communicates, not through MapReduce, but essentially communicates pretty much in real time whenever it wants to that parameter server, and the parameters gets updated. Okay, so this is just one architecture. I want to show you this as sort of one generalized approach. The main thing to keep in mind from this slide is that there's a compute gradient step, and then there is the update the gradient, or we call it the descent step. So gradient, descent, easy to remember. So in the case of a data, again, how are we going to, how do we settle down on this? Okay. And so I want to tell you a little story. How many people have heard of the Seven Dwarfs of parallel computing? Okay, I guess most of you are too young. So I think if you were in parallel computing in the early 90s, you may have heard of this. The Seven Dwarfs of parallel computing, the term was coined by Dave Patterson at Berkeley. He was in a talk by Phil Colella, and Phil told me this story. It comes from one slide. He was working on parallel systems, and he observed the compute as well as communication distribution among the nodes. And he saw that there were 7 different patterns, right? There's all the way from all the nodes have to talk to each other all the time to actually it's mostly compute, and then they can talk to each other once in a while. And at one extreme, that is Monte Carlo. That's what we all know as MapReduce, right? A lot of people don't realize that's just one of those of 7 different patterns. Dave Patterson is very good about sort of summarizing these ideas, and he went back to Berkeley and talked to the machine learning people, talked to the graphics people, and actually came up with another 6 patterns. So actually, today, there are 13 dwarfs of parallel computing. So if you're interested in that, just Google the view from Berkeley, right, by Dave Patterson and other folks. It gives you a very good perspective of all of the different compute patterns that are possible. That's really relevant to my talk here because the decision that we make with respect to Tachyon actually goes across these different patterns. And I'll go into that. What do I mean by that? So here's another aha moment, right? So if I were to stop anybody in the hall who has heard of Tachyon, and I say, what is Tachyon, right? I think you would say, well, it's a memory-based file system, right? It's essentially all of the APIs, you create a file, you delete a file, you store a file. You actually don't know how it's, you don't have to know how it's done. It's just really, really fast. But it's really memory-based, right? And then occasionally checkpoint it and store it away. So Tachyon today is a file system, distributed file system. But if you think about what's happening in data center fabric, network fabric, over the next 5 years, the per node total bandwidth is going to multiply by 100 times, right? Now, by Moore's, that's 10 times faster than Moore's law. Moore's law is 10 times every five years. A lot of that is due to technology like millimeter wave communication, rack-to-rack communication. So when that, of course, latency is also going down to the microsecond range, right? Because a lot of the latency is because of going through the various switches. It's actually not the speed of light, right? The electro-optical switches actually introduce a lot of latency. So if you can have point-to-point, then you can go down to almost speed of light communication. So when that happens, there will be a gradual shift favoring shared memory in the data, at the data center scale, right? Because MapReduce is all about compute, do as much compute as you can because communication is too expensive. Well, if communication gets cheaper and cheaper in the limit, you'll say, well, I'm going to go all the way MPI. I'm going to do my graph as though your memory is the same as my memory, right? So in that future, Tachyon or something like it, but I think Tachyon is very well positioned to sort of flip this bit between a file system backed, a memory-based file system to really a file system backed shared memory, right? So looking to that future, you say, what can we do with Tachyon today, taking advantage of this sort of duality and look at Tachyon as a shared memory infrastructure, because that's where we can store a very large model, right? If you're familiar with Spark, Spark does have this concept of a broadcast variable, but it's actually not really optimized for this kind of workload. Okay, you want to go really easy on the broadcast variable. You don't want to put a 1 gigabyte broadcast variable. So that's how we see Tachyon in this context. So for the rest of the talk, I'm going to talk about the results that we've learned through these 4 different architectures. The first one is just Spark only. Okay, so Spark essentially will do, the workers will do the compute the gradients as well as at the reduce phase, it'll do the model update, right? The next one, we will treat Tachyon as purely storage. Now let's see what happens. So instead of using broadcast variable, we're going to use Tachyon as a file system, and we're going to put the model there, okay? And then we also implement essentially a parameter server approach. So we implement our own HTTP-based server, and it sits there and it listens to the gradients that are being computed by the Spark workers, accumulates them, and then update the model, okay? And then the really cool thing here is, so you heard it here first, right? So we've authored a co-processing architecture design for Tachyon. So in other words, Tachyon today is pure storage, but there's a lot of things you can do. If you add a little bit of compute capability, you say anytime you see this, do the following thing. That's very traditional database principles, right? You've heard, I'm sure you're familiar with triggers and store procedures and so on, co-processors in HBase. So what if we do the same thing there, right? Because it's sort of ideally suited to this problem where Tachyon is storing the model, and then once in a while I'm going to say, hey, here's a whole bunch of gradients I just computed. Just take that and update the model, right? Don't come back to me, right? So if you sort of continue down that, so I decided to show that it's really, even if the results don't show up favorably, it's still really cool to think about it, right? So the coolness factor is very, very high far right. So I'll be referring to Spark only, Tachyon Storage, parameter server, and Tachyon co-processing. Okay, how are we doing on? Okay. I'm going to skip the details of this so that I can get quickly to the results, and then if you have questions, we'll come back to this. But essentially, when we implement the design, or when we design and implement Tachyon coprocessor, essentially we introduce a concept of an observer, right? So there's an interface that says you can register an observer with Tachyon, either master or the worker, and then whenever certain events happen with the file, it will invoke that call. It's very simple, right? So you can observe a file, you can observe a folder, and this just shows where the new code is and what already exists within Tachyon as of today. All right, so Tachyon storage in detail. So a lot of people ask the question, okay, so who does what in this situation? So these things are numbered. Okay, again, I've divided neatly into computing the gradients and update parameter, the gradient step and descent step. You follow 1, 2, 3, 4. Okay, so first, when we use Tachyon as pure storage, we have a model file called model.bin there. Okay, and then the next super step comes along. All the workers get one copy of that file, of that model. And then they compute the gradients based on their subset of the data, based on their data set. And then once they have the new gradients, we go down to the B, the update parameters, essentially. Then the step 3, the various derivatives, and then the workers, because in this situation, Tachyon does no compute at all, right? So then the worker, a new set of workers, does the updating of the parameters, and then that gets reduced at the driver, and it stores a new model back at Tachyon. Okay? So this pointer, very good. Okay, thank you. Okay, what happens, so pay attention to this, right? There's a clear gradient step separate from the update parameter. So these are going to be 2 set of alternating jobs within Spark that goes back and forth. The cool thing about coprocessors is that the gradient or the gradient step, the model update step, is done by Tachyon. So the Spark jobs can run in parallel with what's happening here. Okay, so first, we still have a model file sitting in Tachyon, and that gets distributed to each of the Spark workers, which then computes the various gradients. Okay, now once they have the gradients, they send it back to Tachyon, and the cool thing here is the Tachyon workers now has a coprocessor that says, you know what, I'm going to pick up these gradients, I'm going to update my model. And so step 3 happens essentially asynchronously, right? And well, let me not answer the question. Let me anticipate the question. Let you ask it. Like, does it really work, right? Okay. So this is what I just said. So the Spark workers does the compute the gradients. They handle the data parallel partitions, right? And since they only compute gradients, they finish up fairly quickly, and then they go back and say, I'm going to compute the next. I'm going to pick up the next data partition. So the workers are constantly busy doing that task. And Tachyon is doing it for descent, and it's also hosting the model. Okay? All right, time for results, and we will be good. So you remember there were 4 different architectural options. Of these 4 architectural options, we ran 3 different training sets on them. One is the MNIST data set. 2 is the Higgs and molecular. Roughly speaking, getting larger in each case. Okay, so that's part of our scaling study. So first, constant load scaling. This starts out with 8. We scale by the number of executors, 8, 16, 24. And this is a sort of unitless relative speed. You take the time, we invert it, multiply by a constant so that it starts out right at 8. So this is for the 8 point. So you can see it is sublinear. Okay, it's not like this is 8 and this is 24 up here. And the cool thing is Tachyon coprocessors is one of the best, or in this case, it works out to be the best. And Tachyon parameter server, the HTTP approach, is also very good. Okay, Spark only and Tachyon storage don't scale as well. Okay, and if you take a step back and think about why that's the case, the advantage of these two approaches is that there's asynchronous communication going on, right? This one has to do all the compute and then talk, and then compute, and then talk. So that talk, there's a lot of congestion, right? So that's the reason as you scale up, that congestion gets worse and worse, or get worse more quickly than this case. The training time speed up is really, really cool. What we've done is take the training time, normalized it to the Spark only. So this is really 0, but I had to do like 0.01, so it shows up on the chart. So this is 0 relative to itself. OK, so it turns out the Tachyon storage is actually worse than Spark only, right? And it kind of makes sense, right? For a certain model size, it's actually better to just use Spark broadcast variable, because that Spark does really well with it. If you have to then send it to Tachyon and back, you do the communication between Spark and Tachyon, or Tachyon and any client, incurs a serialization and deserialization cost, right? So that is what that is about. Now, when we go to parameter server, where we have the HTTP service, then we get pretty good speed up, right? 40% here. There's going to be some variation. And the really cool thing is, with Tachyon co-processing, we actually get about 60% speed up for very large models. And again, the reason for that is because we're able to do a lot of things asynchronously. Training convergence. So this is the last chart, I believe, that I show you on these results. Here's the parameter server approach, right? Classically very clean, very efficient. It is the one that converges the fastest early on. But notice, at least for our implementation, it comes out to a minimum error that is worse than the one that we can achieve with Tachyon co-processors. Okay, I'll come back as to why that's the case. But I want to show you the Spark-only approach here and the Tachyon storage approach, roughly about the same. And in particular, they don't converge as quickly as the other two approaches, right? They essentially, asynchronous, this is normalized by time, so the asynchronous approach is superior. What is going on here with all this jumping up and down, but actually settling down pretty high? So how many people are familiar with with the mini batch training, right? So maybe you can explain why mini batch does this, right? So all of these other ones essentially go through the entire training data set and then does a model update. Okay, what you could also do is do a small batch and then update the model, and then a small batch and update the model. Then the question is, does it matter and does it work? So if you think about gradient descent going downhill, you sort of imagine you're on a motorcycle going downhill and looking for the global optimum. If you take the whole data set, you may actually end up at a local, because each time you make a step, it's a fairly large step, right? But if you take a small step at a time, you may actually zigzag your way out of the local minimum and find the global minimum better. But at the same time, because each of the workers is seeing a different subset, there's an opportunity for one to sort of point in the wrong direction. So that's what happens in the beginning, but it does, in fact, find a much better minimum over time. Okay? So lessons learned. So sort of our favorite behavior here is that the Spark, the gradient step, and the Tachyon, the descent step, can be scaled independently, right? So if one workload turns out to be much more compute intensive than the other, then we can have more CPUs working on one than the other. Excuse me. Oops. Now, we actually get mini-batch behavior for free, because each of the Spark workers is effectively a mini-batch. And when it sends the gradients over to Tachyon, Tachyon is not sitting there wait. In fact, we have to do extra work to make it wait for the whole data set to complete. Then, so when it upgrades the gradients almost in real time, we get the mini-batch effect. And as you saw earlier, we get up to 60% speed gain. And it scales almost linearly, and it converges faster. So in fact, we're very pleased to find that our favorite architecture is also the best performing on these measures. As far as data partitioning is concerned, big partition will slow down the convergence, right? Shorter time per epoch. The smaller partition will give you faster convergence, the longer time per epoch, right? And so there's a trade-off. In other words, you can find that there's going to be an ideal data partition size that is a function of your infrastructure load. Memory tuning is also important, right? Because you got to estimate how big is the model, how much of that is going to occupy each of the Spark workers. And if you have low RAM capacity, then you want to reduce the number of capacitors. Reduce the number of executors. What I didn't talk about is that we actually also did, Amazon has these GPU instances, right? So we also try that. Now that, in the interest of time, I didn't go into a lot of considerations there, but the best way to think of about that is it's sort of orthogonal to everything that I've talked about, right? Because the GPU computation is essentially doing the gradient computation. It takes the job of what the CPU would do, and it's doing it in GPU. And so if you do that on a local, that is, there's no network communication, we get up to 10 times speed gain relative to CPU. On Spark, because there is the communication overhead, we get about 2 to 4x faster, okay? GPU memory, at least in the configuration that we find on Amazon, tend to be memory limited. It's about 4 to 6 gigabyte of memory. And so the point here is that there's also a scaling balance between how many GPU you have versus how many CPU and how much memory, okay? This is something that very specific to the infrastructure we work on. We find that GPUs might just fail randomly. And the cool thing is, because of the gradient descent, sort of the nature of deep learning neural networks is actually reasonably fault tolerant, right? It's like if you drop 10% of the data, the training data in one iteration, that doesn't really, you'll still eventually converge. Maybe a little slower. So in summary, and I'll leave time for questions. I think the important point that I try to get across here today, if you remember nothing else about the deep learning infrastructure that I talked about. So our view is that Tachyon is much more than a memory-based file system. It can become a file system-backed shared memory, right? And we've demonstrated some of the advantages, even with current infrastructure, where that is advantageous. The combination of Spark and Tachyon and co-processing, which is something that some of you probably most of you have heard of it for the first time here, yield superior deep learning performance in multiple dimensions that we've measured, the scalability, the convergence speed, and so on. And finally, we are open sourcing both the Tachyon co-processor design as well as the code that does all the stuff that I mentioned here. Okay? That's it. Oh, I forgot, I do want to acknowledge a lot of very fruitful discussion and collaboration with people like Reza of Stanford, a consultant to Databricks, with Taoyuan Li, with Xiaoshan of Baidu, as well as Adam Gibson of Deep Learning 4J. Questions? Yes?
Are you serializing the object communicating between the primary server and themselves? It seems to be that a lot of speed.
I'm going to repeat the question. It's really good. So the question is, and I'm going to, if I'm not correct, then correct me. How are we serializing the communication, the data between the Spark compute and the Tachyon sort of gradient descent? So the direct answer to your question is we're using standard Tachyon serialization to deserialization. So it is really expensive. And so you're absolutely right. And so that's one of the things we're going to do. which is because we know exactly what this data format looks like. We're going to have sort of custom serialization to, as opposed to just very generic Java SerDes. And that will give us sort of a linear gain, maybe a factor of 2 or something like that. Yeah, great.
So you are updating asynchronously the model in Tachyon. So does that create any sort of setup or resolution?
Okay. The question is, because we are updating the model asynchronously, does that create a race condition?
Or the other extreme, which is deadlock, like the inverters are waiting for the model to update.
Right. So I'll answer the question this way. It's a really good question in the following 2 senses. Number one is that if you're familiar with neural networks, actually you don't have to. I can explain to you. If you look at a neural network, right, before it's trained, every node looks just like every other node, right? It's like people sitting in a row like this, and we all look exactly like each other from the beginning. In other words, if you look at the error surface, it's periodic. So it's very easy for like if we all do things randomly, independently, we're going to end up in our own respective local optima and sort of never converge. And so the way we overcome things like that is a sort of standard technique is that there's always a warm-up period, right? That gets you in the right neighborhood, and then you do things in parallel. So you actually you do things serially first. So I don't know, you noticed that the chart that I showed earlier starts at the iteration number 400 or something like that. So there's a 400 iterations where everything is serialized. All right, but that's a really good question. Yes?
Maybe a related approach, because I'm not sure about all the implementation details, but a related topic. Is there any resemblance at all to the Hogwile paper on MapReduce that might be fairly interesting?
Yeah, so the question is this work related to Hogwile? I believe that's Microsoft, right? Yeah. So the answer is yes. So I alluded to that earlier in that, so if you read the Hogwile work, they say, hey, we tried this and it works. We didn't think it, we thought we might get into trouble. So the idea there is that training a neural network to a certain point is actually very flexible. Like you can lose some data and it'll still get to the same place. So that's sort of related to the earlier question where the race conditions, once you're in the right neighborhood, doesn't really matter. We'll eventually converge to the same place, right? So it's sort of an inherent property of neural networks, of deep learning. So Hogwile works for the same reason, right? You just go Hogwile on that's where the name comes from. Any other questions? All right. Thank you.